Okay. Good evening, all. So, how is your preparation regarding the upcoming exam? Any pointers, any doubt, anything you want to ask? Is it okay? Someone wants to say something? Okay, no comments. Fine. Okay, so let's see whether some other students also turn up or not. But as on discourse, we have actually put a post regarding what we can discuss in this last session, most probably, which would be a weekly session. And after that, we will have some revision sessions and something like that, some sessions, but those will be mostly revision based. This is mostly the last session corresponding to weeks, and that's why many one of you told that dynamic programming is something that some of you found difficult to understand. So we decided to do that, and a bit of divide and conquer request also came. So we will also discuss some parts. Yeah. Anyways, any general comments? Anything you all want to say before we start? Okay. Great.
Hello.
Yeah.
Sir, is it necessary for the exam to remember algorithms such as Dijkstra, etc.?
Yeah, see, remember means obviously in terms of end-term exam, you should know how those algorithms work. We would not be asking you to write codes or maybe answer something directly from the code like that. But for OPP and all, those things should be clear, right? Otherwise, how will you code the thing? And regarding remembering the algorithm, see, it's more important that you understand the way how this works. If you can dry run an algorithm, then you can write the code of it yourself. It would take some time to write, but you can write it on yourself. Now, exam actually tests whether that writing you have practiced or not. Because in a limited time frame, it's not expected and it's not possible that you, even if you understand the algorithm, you can write the code of it until and unless you have practiced. So the ideal way you should study algorithms is understand the way how the theoretical thing works. Then actually do not see the codes. Try to simulate the code on your own by thinking in mind how you are solving the algorithm pen and paper. And when you write the code on your own, and let's see if it gives you the correct answer. After that, you practice that code 2-3 times, and that's how you prepare for it. So obviously, for programming exam, you have to understand. I mean, you have to be able to write those codes. But when you say remember, I don't feel quite comfortable with that term. Uh, Practice is something that should have been done. Okay. But for end term and the quizzes, basically, we generally go for the theoretical parts only. You all know that already, right? So, yeah, fine. So let's start the session. Okay. So again, since this is the second time we are doing dynamic programming, I'm just repeating the basic understanding of why we are actually going for dynamic programming in some problems. Then we will discuss the three major problems which has been taught to us in this course. Yeah. So see, the basic idea of dynamic programming came into action when for some problems we could not find any, so to say, an intelligent way to approach that problem. like Dijkstra is an intelligent way to approach a problem. Let's say the greedy algorithms where you choose a specific metric to decide which tasks has to be done in near future, and depending upon that you get an optimum result. So all of these has some proper approach to solve the problem. But for some problems where you do not have a specific approach, or maybe let's say a very intelligent approach to eliminate some part of the problem space and only test on some other part of the problem space, and that's what reduces the time, correct? So when we say that you have to search in an array, right? What you an assorted array, let's say. So what you basically can do is you apply binary search, and what that does is it checks a specific element anywhere in the array, okay, ideally in the middle, and depending upon that, it decides that whether I should check further on the left side or right side. So whichever side you choose, the other side you eliminate. So you have eliminated half of the problem space, right? Half of the problem space, and that's why you get a efficiency in time, right? So that's the advantage. But some problems we cannot do that, and we have to check through all the possible, mostly all the possible uh, enumerations of the solutions, right? And then depending upon all this enumeration, you have to pick up the best one. So in these kind of problem, anyway, it's kind of a trial and error. So you have to check all the possible answers and pick the best among them. So the only possible optimization or increase in efficiency that we can think about this kind of problems is I would not repeat the task which I have done already. That's the motive of dynamic programming. Okay, that I would not repeat the task. Anyway, I have to check all the solutions and pick the best one. So let's not repeat the same task again and again. If I have done a task already, I would not repeat that. So I would store the task, the result of a specific subtask in some place. And later, if that subtask occurs again while in the course of solving that problem, then I would just refer this pre-solved solution of that subtask. That's the idea of dynamic programming, and that's why we can reduce a problem space. Let's say a problem space is there which had some exponential, let's say 2 to the power n uh, different solutions, not solutions so to say, but problem space is the term. Solution is the goal state among the problem space. Okay, so let's say 2 to the power n different candidate answers or candidate solutions, right? Candidate solutions, right? Which is basically your problem space. So among them, let's say you have only n cube distinct n cube distinct candidates, and all the other are actually getting repeated, right? Candidates. All the others are getting repeated. So if you can simply refer whenever the repetition happens, right? So 2 to the power n minus n cube, these are all the repeated subproblems. Repeated subproblems. So whenever these 2 to the power n minus n2 things occur, you can just simply check whatever is the result when you calculated it for the first time. Right. So essentially your algorithm boils down to some function of n cube. I'm writing some function of n cube. The reason for that is if you have n cube distinct sub problems, then let's say to solve a particular sub problem, it takes n squared time or n time. So you would end up with n cube into n, which is n to the power 4th time. But be there as it may, it is some polynomial time. It's not exponential. Correct. So that's the idea. So you would only use time for calculating the solution of the distinct subproblems. And that's why dynamic programming has two important properties which must be there in the problem in order to apply dynamic programming on that problem. And that is your optimal substructure, and overlapping subproblem. Okay, so overlapping subproblem. So if overlapping subproblem is occurring, that means this thing, whatever I discussed over here, that means overlapping subproblem. That it's overlapping, it's happening multiple times. And optimal substructure is essentially the idea of how a greedy algorithms work, that you basically pick the best available option in order to solve the big problem. So here it's slightly different, but the idea is kind of similar. Optimal substructure means you actually try to solve the subproblem in the best possible way, which actually contributes to solving the whole problem, the big problem, right? The main problem in an efficient way. So solving the sub problems in an efficient way also helps with solving the big problem efficient way implicitly, in an efficient way implicitly. But many algorithms would not bear this property. So I think I mentioned that in one of the session, or I don't know, in discourse most probably, that many algorithms are there, and we have given some examples. So let's say longest path algorithm, right? The longest path in a graph, or let's say the longest path even in a DAG, if you check, right? So that would not work when you divide the graph into separate parts or sub problems. Okay, but the shortest path can work depending upon some modification that we have to do in the general shortest path algorithm. So generally speaking, many algorithms would not bear this optimal substructure property, and in those algorithms we cannot apply dynamic programming. Okay, because in dynamic programming we solve the sub problems, and then on the solutions of the sub problem we proceed further to solve the next problem, right? So unless and until we have the solution for any prerequisite sub problem, right, we cannot solve a specific sub problem. So let's say I solve, you all know that already from the discussions previously for examples of matrix multiplication, or let's say subsequence, longest subsequence. We will again go to them and discuss once more that let's say there a table like this, the matrix was there for subsequence, and let's assume this was the table, and let's say you have to calculate the value over here, then you must know the value which is over here. Okay, and also you must have the value here and here. So you need those values. Unless and until you have those values, you cannot decide. So let's say edit distance, same. So for edit distance, you need to know the value which is in this cell, in this cell, in this cell, right? If you have these three cells value, the solution, right, then only you can calculate this one. Okay, we will again revisit those, but I'm just stating. So what does that mean? That means that this was one subproblem, this was one subproblem, and this was one subproblem. These three subproblems you had to solve earlier in order to solve this. Okay, so that's the idea, which is optimal substructure, that you solve a subproblem, you also incrementally contribute something towards solving the larger problem. Okay. So these two properties of dynamic programming are the essential properties. Fine. So that was the basic intro. Now let's discuss the algorithms now. Memoization and dynamic programming are two different things, but kind of the similar idea only. That has already been discussed in the lecture by sir in detail. I'm not going into that much detail, but the idea is memoization is whenever you are encountering a sub problem, right, then you are actually trying to again call a function, and then so basically whenever you are encountering a sub problem, you are trying to solve it. You are not you are not proceeding in a way where you have solved the problems which were required as a prerequisite. You are not thinking about the prerequisite. So like in just the example we discussed over here, uh, these three problems were the prerequisite for this one. So I have to solve these three problems first, and then only I would come to this one. And that's why in edit distance, the matrix, right? We traverse the matrix starting from this particular cell first, and then the last cell was this one, right? So we traverse the matrix in a back to front manner. So that's why, because for every node I comma j, sorry, not node, every cell I comma j, I must have the value of I must have the solution for I comma j plus 1, and I plus 1 comma j and I plus 1 j plus 1. Don't worry, we would again discuss that for any distance, but these three solutions I must have, which are essentially these three sets. So you are calculating the prerequisite first and then going to another sub problem. That is the dynamic programming approach. Memoization approach is just the same thing. The only thing is that I would not worry about solving the problems in a manner such that the prerequisites are covered first. Rather, I would just call the problem and it would again recursively call the other sub problems which are required for its solution. Okay, so at first, memoization would directly call this sub problem. And essentially, when we see that this subproblem requires the use of other three subproblems, then again a function call would happen with this problem as the next recursive call, and this problem as the another recursive call, and the third recursive call with this problem. Now let's say this problem again needs the solution of this problem, and this problem. Correct. So again, the recursive call like this, the chain of recursion occurs until we go to a base case. So memoization is mostly about recursion and not proceeding in a way where the pre-requiring subproblems are solved first, but we solve the problem whenever we encounter them, and in the process we call multiple recursive calls. So that is memoization. Okay, so any memoized program you would see for the same problem, you would see that it uses mostly recursion, whereas dynamic programming, same thing, right? Just the same thing, two different names. And dynamic programming, rather, it does not use recursion, but it mainly uses a 2D array to solve the problems. Because we are using a 2D array, and in that 2D array, we will at first solve those subproblems which are required first, and then proceed accordingly depending upon the prerequisite. Fine. So these two are the basic reference. Now this is just an example of the Fibonacci function which sir has discussed. You can check that. Okay, grid path is again a motivational example. So it's not something that is directly used in dynamic programming, but for the motivation we have discussed that. From your exam point of view, both for your OP and for your quiz, the other three algorithms are very important. So we would start the discussion over there. And if you want to understand the grid path problem, I would again request you to check the open session of this particular week along with the lecture. Okay, so now the longest common subword problem. Okay, so what does it means is so let's take any two words. So let's say W1, a word is fine, and W2 there is another word. Fine. So these are the, let's say, two words, and we have to find the longest subword which is common between them. So if I see over here, the longest subword that I can check is that I can find is, let's say, ACGC is over here. Here also I got ACGC. Fine. So how can we check that? So the basic way to solve this problem is you have to check both the strings, traverse through both the string from each index, right? So I would at first put my checking from here and from here and check whether it is equal or not. If it is not, again I would travel here and compare it with this one now. Still it is not okay. Now I would travel here and then again compare with this one. So like this, I would proceed and check one by one. And with respect to each of the character over here, we would check all the characters over here, starting from every starting position. Correct? But obviously, as you can understand, that would take a lot of time. And so we have to use dynamic programming to solve this problem. So now let's check that, how to do that. So every dynamic programming, what we do is basically we discuss that we have some prerequisite subproblem, right? So here like that, we discuss the same thing, that I must have the solution for the prerequisite subproblem. So what does that mean? That means basically you must have a inductive structure, or so to say, you must have a this substructure we call na, the optimal substructure. So the sub problem should be defined in terms of other sub problem. Correct. So we would try to come up with a inductive structure, inductive formulation of given a sub problem. What are the other sub problems on which it is related, on which it is dependent upon? Okay, so that is given over here. This thing, that longest common word ij. So LCW ij is basically the matrix which is storing. When I say LCW ij, it means that W1 strings I and W2 strings j, considering, let me just state it, considering okay, so this is what LCW of I comma j means, considering W1 is at index I, that is basically we are traversing W1, right? So that traversal is done by, let's say, a variable I, and it is on some value on W1. So some position on W, it is on some position on W1 string, and J is on some position of W2, right? Basically the J position itself. So I and J are markers which is traversing on W1 string and W2 string. So when I say LCW of I comma j, it means that wherever I is in W1, so let's say if this is W1 and I is over here, right? And this is W2, and let's say J is over here. So that means whatever is after that, right? Whatever is after that from J in W2, and whatever is after that from I in W1, within this part, this part and this part, right? Within these parts, what is the maximum common subwords length? Fine. So this is equal to your LCW of ij. Fine. Now we have to understand how we can formulate the structure. That is, so first case is if I check I and j, right? So I is traversing on W1 and j is traversing on W2. So I check I and j, and if I get, let's say, I is equal to j, correct? That I and j matched. So what is my next task? My next task is I will check the next element, right? Because I and j both has matched, so I would check I plus 1 and j plus 1 characters. If they also match, then I understand, yeah, that is correct. I mean, the next characters also match, and then again I would proceed. Okay, so what would it mean in terms of the structure, the inductive structure that we are talking about? If this W not I equal to this, sorry, what I mean is if W1 of I is equal to W2 of J, right? So we have a matching, correct? So then we will have some condition. So we will write it over here. And second case is when my W1 of I is not equal to W2 of J. Then what will I do? So if you check the condition over here, just check that if there is a match, correct? If there we have a match, that is AI and BJ written like that. So if Wi is equal to W1 of I equal to W2 of J, what we would do is we would do 1 plus LCW of I plus 1 J plus 1. So why are we doing this? That is, we know that a match has happened till I and J, and we would go to the next two characters, right? We just discussed that. I would increase I and J as well. So whatever is the maximum length string that I have, sorry, maximum length subword which I have up to I plus 1 and j plus 1. With that, I am adding plus 1 because I and j are also same. So if you are not getting it, let me just restate it. So I plus 1 means over here, correct? And j, just a second. Yeah. So I plus 1 means this position, correct? Because I is over here. So j plus 1 means this position. So assuming that W1 of I, so this is W1 and this is W2, if W1 of I is equal to Wj, I would, what I would do, I can say that in that case, suppose I have been already told that the max, that LCW of I plus 1 comma j plus 1 is equal to, let's say, beta, some value. Okay. So what does that mean? That is from here to the end and from here to the end, correct? The maximum common subword which I have is of length beta. That has been told. And now I have checked that W1 of I and W2 of j are also equal. So what can I say, that if that is the scenario, I can simply add 1 with beta, because till this place, right, till this place, the maximum common subword length was beta. Since I and j, since these two are also equal, so I can just say that LCW of I comma j is equal to beta plus 1, right, which is essentially your LCW of I plus 1 comma j plus 1 plus 1. Fine. So that's what has been discussed over here, this condition. And if it does not match, then you don't do anything, because you know it's not a match. So LCW would be 0. Fine. That is the longest common subword does not exist. 0 means what? There is no, I mean, there is no string common between I and j. I mean, in the word W1 and W2, when I is from the I position of W1 and from the j position of W2, we do not have any common word. Correct. So that's it. So simple recursive structure, and then you simply code it up into a table. Sorry, not table. Not table. You simply code this recursive structure into this code. So what do we have to basically do? Understand. We have to just create a matrix like this, correct, in order to compare. Okay. So let's assume that the top of the, I mean, the columns of the matrix represent one word, rows of the matrix represent other words. In your mind, you should think it like that, that it should represent. And simply after that, what you have to do is just apply the recursive conditions. That's it. So that's what has been done over here. And initially, since we are doing summation, right? In the example, since we are adding 1 plus LCW of I plus 1 j plus 1. So since we are doing summation, subtraction, this arithmetic operation, whenever you have to do, please initialize your array with 0. So that's why we have done the initialization with 0, like this over here. Okay. And why we are taking m plus 1 and n plus 1 length? That's also something. See, m plus 1, n plus 1 length is taken just to give the boundary condition, right? So we are doing LCW of ij is equal to like this. LCW of ij equal to 1 plus LCW of I plus 1 plus j plus 1. Now, so basically to calculate ij, I must have I plus 1 j plus 1. Great. Now when I plus 1 j plus 1, I must have, to calculate I plus 1 j plus 1, I must have the answer to LCW of I plus 2 j plus 2. So like this it would continue, but at some point it must end, right? So at that point I must have a boundary condition. That boundary condition is when I have reached the end of the string, right? Both the end of the string, then I can see that obviously there would not be any match, right? So that is actually this thing. If you see, the string secret is over here. So this is just a blank cell, and that's why all the entries over here are 0. There is no common value. Likewise, this string also, here it is empty, which means that we have reached the end, and that's why there is no common value, and that's why the length is 0. Now, when we reach over here, by doing plus 1 for any one value, we would do 0 plus 1, right? But if you, if so, that's why we should initialize the boundary conditions with some value appropriate to the problem. Here in this case, we are doing summation, so we are initializing it to 0 at first. So n plus 1, this plus 1 more is taken just to represent this fact to initialize the boundary condition when we have actually overpassed the any one of the string or both of the strings. Okay, and then simply whatever you do is, since it's a 2D array, so you need two loops, and depending upon the condition in which you are proceeding through dynamic programming. So here we discussed that the condition is I plus 1, j plus 1. So in order to calculate ij, you need I plus 1 and j plus 1. Correct? So you should solve I plus 1 and j plus 1 first. What does that mean? Where are, in which part of the matrix this plus 1 and j plus 1 area would be there, right? So it would be at the rightmost bottom. So you should start your work from the other way, not from the 0 0 index, but from the last mn index, right? The last index. And because if you calculate the last one, then you can come to the previous one, right? Because in order to calculate ij, you need I plus 1, j plus 1. Correct? So that's what you are doing. Yeah. So that's why these two loops are actually starting from the end index. Okay, and then we are modifying it by -1 -1. I mean, sorry, not modifying, reducing it by updating it by -1 -1, just like that. Finally, and this thing is just the same thing we discussed. In dynamic programming, once you formulate this inductive structure, then it is very easy. So only thing is S1 R is equal to S2 C. The same thing we discussed. W1 I is equal to W2 J. If that if that is the case, you simply add 1 plus the this concept which I just discussed, this one, right? So you just apply that, or else if it is not equal, you set it to 0. Sorry. Okay, so and that's it. And then you simply return the maximum value LCW of RC, provided it's greater than max W, the last maximum value. Okay. So yeah, so that's the simple thing. That's how you get the longest common word. Now the thing is, this is a bit more involved example, which is the longest common subsequence. Okay. Now, what does a subsequence mean? A subsequence means that here we actually considered a continuous string, right? So the example that we took over here was this one, that ACGC is common in both the strings and the largest common subword. So it should be continuous. It's kind of substring, right? Subword, substrings are same thing. But subsequence is a bit different concept. Subsequence means that you can have discontinuous, but the discontinuous character, but the sequence must be preserved. So what do we mean by that? If I have W1 equal to, let's take the same example only. So this one only, right? This ACGC, USRT, and DBA, GCAC, DCT. So in this example, let's say I take a string A, G, T. Right? Suppose AGT is a string. Okay. Now I can see that A is over here, correct? G is over here, and T is over here. Fine. So what happens? Can I have any? I mean, do I have A, G, and T proceeding in this direction only in W2 as well? If I see A is here, I have two possibilities for G. I can consider this one or this one, anyone, no issues. Okay, and then at the end I also have T. Okay, so I see that AGT is a common subsequence between both of between both of them. But let's say if I write Okay, AGR. So AGR you got over here. A is here, G is here, and R is here. Correct. But I do not have AGR over here. I can have A. Then let's say I take this G now, G, but no R after that. Fine. Even if I, let's say if I would have R over here, oh sorry, yeah. So let's say even if I would have R over here, then also it's not a subsequence. Why? Because A is occurring for the first time over here. I must have A. Here we had A, G, and then R. So I started A from here, then I took G, this one or this one, any one of them you can consider. But after A, there is no R, right? So I can take A from the second string, G from the second string, but no R is after that. R was there initially at the front, but initially A was not there. I must have A at the first, correct? So subsequence means it must be serially located in the string and it should be common between both the strings. Okay, but it can be discontinuous. It must not, it may not be a continuous sequence of character which is common. Continuous sequence of character which is common, that thing we call subword or substring. So it is a bit more complex thing, but not very difficult when we understand the inductive structure. So again, what is the change that we will do in this example is, so we had the longest common word, right? So just assume that all the things remain same, everything remains same. Only thing is we have to change the inductive idea that we had, the formulation of the inductive structure. So initially, what did we have? We had LCW, right? I'm just writing LCS now since it is subsequence. So it is I comma j. Assume what did we have for LCW? We had 1 plus LCS I plus 1 j plus 1, provided it is equal. When my W1I was equal to W2J. Fine. Or else it was 0, the other case. Okay, so this was in terms of LCW. I'm just starting from there. Now here, if we get a mismatch, then does that mean it's a 0? I mean, so here in the example that we took, right? Here. So the other example, AGT, right? AGT was there. So A, G, T. Here also we got A, G, T. So whenever we had A and G, right? So let's say we are at a position when we are searching for T, correct? So I would get a mismatch of T from here. I would get a mismatch of T from here, from here. But all of these would be mismatched after AG. Even this C would be a mismatch. So all these 1, 2, 3, 4, 5 characters would be a mismatch with respect to T, right? But in case of substring, I would have made them 0. But now I cannot make them 0 because only thing that matters is whether T occurs even once in the sequence after AG occurs in the string. So I have to go till the end, unless and until I go till the end, simply by checking one particular position's inequality. I cannot put 0 like what I have done in the longest common subword. Correct? So I have to go think till the end. So how will we actually do that? So if there is a match between the ith and jth element, correct? So then I know it is 1 plus, I mean the length of the substring, sorry, subsequence is 1 plus whatever the longest common subsequence was there, one character before. I mean the example we discussed over here now, this one. So if I have been given that the longest common subword till this area is already been given to me till these two areas, right? And I am currently over here, and in this string I am over here. right? And if I know that these two matches by an if condition, I have checked that these two matches, then I can simply write, okay, I already know the maximum length of the common word or common subsequence till this value, which is already given to me, which is beta in our example, right? And these two values also matches. So I can simply write, if I consider this whole string, right? Then this whole string's maximum common subword is 1 plus beta. That's it, because it is matching, this one value is matching. So that's the idea. So in subsequence also, if there is a match occurring, I mean, that means that, okay, there is a match. So whatever is the largest common subsequence, just one character before, I can add one value with that because the current character is a match. Okay. So that's why this holds, no problem. What does not hold is the inequality, which we discussed just now, that when it's unequal, you cannot make it zero because there is a possibility that that character might occur later in the string in subsequence, correct? So what we would do when the condition is w1 of I is not equal to w2 of j, right? So in this scenario, what we would do? See, the idea is now there can be two possibilities. That first possibility is I might have, okay, so let's consider these two strings, right? So w1 was let's say a1 e2 dot 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 an, okay. So I see that currently my ij, let's say both of I was over here at a2, and let's say j was over here at b3, suppose. That is j is 3 and I is 2, suppose, right? And I am checking for their equality, whether these two are equal or not. Fine. So I get that they are not equal, they are not same, not the same character. Now the subsequence can be checked in two possible ways, right? I have to check for longest common one. So I can either check a2 with the next character in b, or I can check, so basically I can check a2 with b4 over here, okay, in order to understand whether, let's say, if there is a greater match, or I can check b3 with a3 over here. So there are two possible scenarios of the next match that I may check. That this one is not matching, but let's check the next step. Okay. So what I can do is I would write we are finding the maximum value, correct? Maximum, the longest common subsequence. So when there is a mismatch, I have to check the value of the other two possibilities in that case, and that would be my maximum of longest common subsequence of either I is increased and j remains constant, which essentially means you are comparing A3 with B3. So j remains constant on B3 itself, but A3 is now tested. So A moves forward, this one, right? Or LCS of the other one, that I remain constant and j increases. Fine. I have two possibilities to check whichever one would give me a greater value, correct? So I would state that, okay, ij is equal to that one, because itself the index position I and j for w1 and w2 are not matched. If you see over here, it's max of LCS of I plus 1 j or LCS of I j plus 1. So again, you see, this is the only change that we did in the not matching condition. In that case, even a single match would fetch 0. Right? If we go over there in the previous case of longest common word, a single mismatch gives 0 because the continuous sequence of match matters. But here it doesn't matter. Right? So we change this condition like this. So the idea is we would go till the end of the string in both ways. For both the strings, we would go till the end, because even the character which we are searching might occur sequentially at the end. Okay. So yeah, there is no further change in the code, just the same code that we wrote for subword. Only thing is that now you have to modify this else condition. Okay, the else condition in initial case was 0. You are setting LCW to 0. Okay. And in the longest common subsequence, you are setting it to be the this formulation that we discussed. Is it clear? Any doubt? Any doubt in the code? Any doubt in the concept? Okay, fine. So after that, we are coming to the edit distance. So edit distance is a bit extension of the previous concept which we discussed about the longest common subsequence. Edit distance mainly means that how much changes you have to make in a given string in order to make it to the other string. Okay, how many changes, and you want to obviously minimize the changes. So edit distance of ij, right? The LCS of ij, what it gave? It gave that from the start of ith position in word 1 and the start of jth position in word 2, LCS of ij matrix stores the value which is the common and the longest subsequence considering the position that, that we just mentioned, right? But edit distance of ij means that considering the first string starting at position I and j starting position as j for the second string, what is the minimum number of changes required in order to make the first string, the W1, into the second string W2. Okay, how many changes are required and how to minimize that? What is the minimum number of changes required? That's what edit distance of ij means. Okay, now again same concept. Simply you have to create the two-dimensional array for the two words, and then only this formulating this concept is what is essentially dynamic programming. After that, it's CV. So let's also discuss the edit distance once. Fine. So see what happens is in the edit distance. If I have, let's say, a string called let's say Marburg. This virus is coming now, Marburg virus, one which is discussed now. So let's say one string Marburg, and I have another string. Let's say markdown. Okay, now this is my word 1 and this is my word 2, and I have to make word 1 into word 2. Okay, so let's start from the beginning. I am over here in M, over here. So this is I and this is your J. Correct. So let's check now if both of them matches like in this example, both of them actually matched. So how many changes required to do on W1 in order to make it into W2? Considering only the first case. So what I mean is, if I only have to consider the first character, then no changes are required, right? So no changes are required. But we represent it in the form of programming in a different way. So the array which is used, it represents it in a different way. Give me a minute, just a second. Okay. So yeah, so I was saying that it is represented in a different way. So what is the different way? The different way is when we write edit distance of I comma j, it basically means starting from I. So this is a common mistake which I saw in many of the students' idea or understanding, that edit distance of I comma j, it means not only considering the ith and jth position, it means from I till the end of the string and from j till the end of the string. Okay, in terms of programming, I am saying, right? In terms of programming, when we write ed I comma j, it means from word 1's ith position till the end, and from word 2's jth position till the end, right? How many minimum number of changes has to be done in order to make W1 into W2? So when I write, so in this case, I and J, both of them are at 0 position, correct, in our example. So when we write edit distance of 0 comma 0, it essentially means your answer, the solution. That is your, what is the minimum number of changes required to make in the whole string, because from 0 means starting from 0 to the end for both the string, which is essentially the whole string. Okay. So if I say you that edit distance of assume that this is the length m and this length is n. If I say you edit distance of m minus 1 comma n minus 1, then this actually means only the last two characters. Fine, because it means starting from m minus 1 till the end. Now m minus 1 is itself the end, so it means basically the last character. So what, how many changes is required to make in order to convert the last g into the last 10? That's the that's the value for edit distance of n minus 1 n minus 1. Okay, so you can say that you can simply substitute it or delete it or add it, whatever you want to do. But I mean, substitution is the best case in this example. So simply substitute it. Okay. So accordingly, so this idea must be clear. Do not confuse this simple thing. Edit distance of ij does not mean how many changes required to make I into j, I mean w1 I into w2 j. Rather, it means how many changes required to make W1 starting from I to the end of W1 into W2, considering W2 starting from J till the end of W2. Okay. Okay. Fine. So let's now come back to the discussion. So our algorithm actually, that's why, starts from the end. Okay, not from the start like this. So we would, since we know that again edit distance, uh, okay, so okay, we would come to that later. Just a second. So how the algorithm works is, we would start till the actually from the end only. So can assume that what is n over here and what is g over here. So let's say g I and this is j. Fine. So we start the index j equal to n minus 1 and I equal to m minus 1. And from there we decrease by minus 1 each step till we we go till just before minus 1, that is basically 0, and we decrease by minus 1 in each step. This is basically your for loop syntax. Fine. So we start from the end because that ensures that I am proceeding one by one, right, from the end. Because if I start from the starting, then I must have the solution for the rest sub part, right, this part. But I do not have that. So we will start from the back side. Okay, fine. So how many changes required to make G into N? So that's one, you can just substitute it, right? Again, after that, if there is not a match, right? If there is not a match, then what is the step that we would do? Now, in this case, we told you it's one, but it might not be correct. Why we are saying it might not be correct? The reason is, in this case it's okay, but in the middle it might not be correct, because we don't know whether substitution is helpful or addition is helpful or deletion is helpful. So when you have to make a string a1, a2, a3 dot 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 am into a string b1, b2, b3, bn, right? You can change each of the characters wherever a mismatch occurs by simply substituting that character with the character of B, or you can add a character of B and consider the next one, or you can delete the character of A and consider the next one. So what I mean is three solutions which sir has again discussed, till I am just mentioning. First one is substitution. That substitute. When all of these cases are occurring, when a of I is not equal to b of j. Okay, or in our example, w1 of I is not equal to w2 of j. So substitute. If I substitute w1 of I with w2 of j, in that case, I only did one operation. And what is the next step that I would do? Since already the substitution is done, so let's say this is the substitution. This was not matching, and I have already done substitution. Right? So now these two things are equal. Now, since these two things are equal, the only thing that I have to do is proceed to the next step, right? Because this is done, only one operation we did and it has become equal. Now let's check what is the next, where is the next mismatch occur. So you would proceed, right? So both I and j would increase. So we would simply write edit distance of I plus 1, j plus 1. Both of them increase. Second case is addition. So if our w1 of I is not equal to w2 of j, or basically I not equal to bj, correct. So what we can do is we can add the character which is not matching. Okay, one another important concept is whatever changes we do in the w1 string. We do not do any changes in w2 string. Our motive is to convert w1 into w2. Don't do the changes in w1 and w2 haphazardly. We would insert, delete, and substitute in w1 itself to convert it into w2. That's the idea. Okay. So addition means adding into w1. So whichever value, let's say b3 is not matching with a3, correct? So what I can do is I can simply add over here b3. Fine. I added b3 and that's it. And I can assume that okay, so a3 and b3 are now matched. So now my next step would be next proceed. Correct? So when I do addition, that means I have already added, and that's why this character is yet not checked, right? It was missing. It might be a3 may match with the b4, which is the next character. b3 was not matching with a3. Fine. So I added b3 explicitly. Okay. But now what I have to do is, what is the next logical step? The next logical step is I would compare A3 with B4, because A3 might match with B4. It was not matching with B3. I added B3, but now A3 might match with the next B, which is B4. Right? So I would check that. So what I do is I plus 1, sorry, not I plus 1. I remains as it is. We can do J plus 1. Okay, depending upon your assumption that whether you are making changes in W1 or you are making changes in W2 or where you are adding, right? All this plus 1 and whether you are doing I plus 1 or whether you are doing J plus 1 in case of addition or in case of subtraction, these things might change. Okay, so understand the concept properly, it should be fine. And the third one is subtraction. Just the other thing. So if there is A3 is not matching with B3, remove A3. So if we remove A3, that means we have deleted the problem of the mismatch. A2 was here. So we have deleted A3, but now B3 has yet not been matched with at least someone, right? So I must still check whether B3 is matching with the next possible character which is there, which is A4 over here. Correct? So now B3 does not change, but A4 I have to compare with B3. This one. Correct? Because I have deleted A3. So in that case, ED would be A I am moving forward, right? So A4 with B3 itself, which was initially. So J remains constant. So these three possible operations I can do on two strings in order to make one into another when there is a mismatch between the characters. But if there is a match, then no operation. Correct? Then no operation is required. So what does our recursive structure boils down to? So ed of I comma j, please keep in mind this concept of what does I comma j mean, equal to, if there is a match, right, then simply ed of I plus 1 j plus 1. I mean, no changes required. Whatever changes had been needed to convert from I plus 1 to j plus 1, that is just from the previous step, I also need that much changes because myself I and j is equal. I mean, the position I and j are equal. So whatever you needed, whatever changes you needed earlier, that is the same number of changes is needed considering me as well. Me means the ith and jth character in W1 and W2. Fine. So that's why this is the answer. And when there is a mismatch, so when there is AI is equal to B of J. But when there is a mismatch, then I have to actually apply either of these three operation, and that's why my value of ED would increase, right? So what I can write is 1 plus. All of these are single operations. Substitution is a single operation, addition is a single operation, subtraction is a single operation. So I would write 1 plus, right? ED of, now the thing is, see, depending upon which of the operation I choose, whether I do choose to substitute or add or subtract, that also changes the course of choice for me in the future. Because let's say if I added something and that matched with the second one as well. So let's say, let's consider a subpart of the string, something like this. Okay, let me think. Fine. And let's say here it was something like C where it was not matching with A. Okay. And yeah, fine. Now see, C, B. Suppose these two are the strings, correct? Now you are matching from A and C, but A and C are not matching. So you decided, okay, A and C are not matching. Let's make it, let's do one thing. Let's make C into, sorry, let's do the substitution, the first operation, correct? Let's do the substitution. You decided. So I would make C into A because I would always convert W1 into W2, correct? So I would make C into A. So I do a substitution of C with A. And what I get now is, so C is now become A. Correct. Fine. Now I would move both of them to the next step, right? Substitution means I plus 1, J plus 1. Since there is a match, now I would move both of them. So now I come over here and here in this string I come over here. I again say B and C, both of them are not matching. Correct. I again decided, okay, fine, again do a substitution. So I made B into C. So B has been changed into C. Again did a substitution. So two operations already did. So I see, okay, CC done. Now since again I did a substitution and both of them are now matching, this C is matched with this C now after the substitution. So I would proceed plus 1 plus 1. Both of them would increase, right? So plus 1 I come over here which is empty, right? Because I have reached the end of the string of W1 and here I have come till the end of the string on the last character of W. So I see that there is no string in W1, but I have to make W1 into W, right? So what is the operation that I would do? Addition, right? I would just add one character which is B. E is not here, it's empty, so add B. So I did one operation and added B. Correct. So we did how many operations total? 2 substitution, 1 addition. 3 operation I had to do. Correct? In this strategy. But now let's go back to the previous example of what we had earlier. CB, right? Okay. Now see, the first A and C did not match, and then I decided to substitute C with A. But what happens if I do not do the substitution? Rather, what I do is do an insertion at the first one. Okay, so I decided, okay, A and C are not matching. I can choose either of these three operations, right? So I choose the addition operation. I said, let's add A. Okay, A is not matching, correct? I need to convert C into A. So just add A. So I add an A over here. See, the beauty now you get is you did not know what happens in the future, but you added an A, and now you are saying that okay, I added an A, so that took me one operation. But after that, C matches with this C and B matches with this, right? So the same thing, I just took a bad choice of choosing one of the three operation at first, and that's why I ended up with doing three changes to make the same string uh, convert into the other one. But in this case, I just did only one proper operation, and that actually automatically converted my first string into the second. Okay, so you get a much lesser value, right? Much lesser number of steps to be done. So that's why choosing the operation is important. It's not arbitrary. Which operation you do, that is something which is important. And now how to decide that, which operation to take. Simply you don't decide. There is no algorithm to check that. That's why we told that dynamic programming is used when you are not able to solve a problem in an efficient manner. Only optimization that you can do is just do not repeat what we have already done. That's the only optimization. So we don't have any other choice. We would enumerate all the solutions and pick the minimum one, the best one. So what you basically do here is you write minimum among all the possible, uh, I mean, possible problem space values, which is essentially your matrix values. That is minimum among the three operation, right? ED of I plus 1, j plus 1, substitution, comma, ED of I plus 1, comma, j, comma, ED of I, comma, j plus 1. All among all of these three minimum, whichever is the best one, you just pick that one. I pick that one and plus one. Plus one is for the operation, right? So whether you do substitution or addition, or sorry, this subtraction or addition, whichever you choose, right? You that's basically one operation. So that is one you are adding. One plus minimum of this one is stored in ED of I. Fine. So ED of I plus 1, j plus 1, how many, whichever number of operation was required plus 1 for EDI. ED of I plus 1 j plus 1 gives you ED of ij. So in order to edit the string W1 starting from ith position till the end into the string W2 starting from jth position till the end, we need 1 plus the minimum number of operation required to convert string W1 starting from I plus 1th position till the end to W2 starting from j plus 1th position till the end. Okay, or the other two, whatever. I just repeated the thing so that please listen to it, and I hope that should be more clearer. So we just use this minimum inductive structure, add one, and that's it. Simply write a 2D loop starting till the end. Why we are starting from the back side? Because we discussed that fact over here, right? In the first part, that you need this plus one everywhere. It's plus one. That is, you need, in order to calculate ij, you need the next I plus 1, j plus 1 values. So that's why our boundary is located towards the outer side, that is towards the back side. So that's why we start the array from here like this, not from the starting, right? Not from here, from here. Okay. Any doubt or no doubts? Oh, if we go to the code, you see simply. Okay, one more point I forgot, the boundary condition. So in this case, the boundary conditions are a bit different. see in the example like this example when we discussed, right? The ACV, the CD, ACV example. So here we had reached the end of the string over here, right? So in initial cases of subsequence and subword, we discussed that when we reach the end of the string, it's zero because there is no match. Obviously, it's zero. We have ended. But here the question is not about matching. Here the question is about if there is a mismatch, how many steps are required to convert it into the other one. So if there is a blank, that is as good as a mismatch, and that's it. It is a blank means it is a mismatch. Okay. So when there is a mismatch, obviously that means you have to add the things, right? When there is a blank, that means there is no other operation possible. You cannot subtract or substitute, right? So you must add whichever is missing. So here B was not there, so I added B previously when we took the other way. So B we have to add. So whenever you reach a particular string end and the other string is left over, so whichever portion, whichever number of character is left over in the other string, you simply add that, right? So if I am at ith position over here, let's say over here I am at jth position over here, correct? And let's take here. So I have completed traverse the second strings up to J, and first string I have already reached the end, right? Where it is blank. This was not there. So we have reached the end. So in this situation, I must add these characters, right? Whichever is there in the right part of J. So how can I understand how many are left in the right part of J? So if the length is whatever the length is, right? The length of W2 minus J. Right? J means like this up to this point. So what length of W2 minus J, I get this part. Whichever number of characters. That much characters I have to add over here. Which is basically that many operations I have to do. So when the string reaches the end of any one of the string reaches the end, your I or J is equal to M or N depending upon which one it is, you would do M minus I or N minus J accordingly. Fine. If you see over here, M minus I and N minus J, we are doing if initially, and then if it is, the initial start, right, when you are actually starting from N minus 1, at that initial stage, you are making it N minus J and N minus 1. The boundary condition setting. So there we made it 0. Here we should not make it 0 because here mismatch means you need to make so many operations. Correct? Yeah. So we did that addition thing over here, and then the normal thing starts. If there is a mismatch, you don't do anything, just proceed. The ED of ij is equal to ED of I plus 1 j plus 1. No addition, nothing. But if there is a mismatch, then you have to do some operation. Now that is the minimum among the substitution, the addition or subtraction. Fine. And that's at the end you are returning ED 0, 0, because again we discussed that 0, 0 means starting from 0 till the end of the string of W1, how many changes we have to make in order to make it into the string starting from 0 of W2 till the end of the W2 string. Fine. So returning that. Nothing much in this code other than that, just the same thing we discussed. Achha. So I hope if you understood this small example of ACB, this one, I hope it must be clear why edit distance 3 operations are important, right? And there is an important decision among choosing them. Fine. Any doubt? Please ask if you have any doubt about this. Okay, great. So the next one is matrix multiplication. We'll discuss that. So regarding matrix multiplication, in the previous session when we discussed dynamic programming, I have discussed a lot of uh, I mean the part which comes before the inductive structure and all. So what is how you do matrix multiplication, a chain of matrix multiplication, what are the multiple ways in which you can do partition the matrix multiplication, right? So all those things we will not discuss. Mostly the inductive structure and the basic part we will discuss now. So, so basically the idea is since we have to multiply multiple matrices. So A1 into let's say A2. Yeah, we have to multiply the four matrices given over here. Now, since matrix multiplication is associative, we can associate in any way. So I can do like this, right? Or maybe I can do like this. Okay, any of the possible way I can do, and whichever is the minimum, that must be provided as a result of your matrix multiplication algorithm. You must tell me that what is the minimum number of matrix multiplication required to do the to do multiply these four matrices. Obviously, if you do these orderings differently, right, then the number of matrix multiplication also changes, and we are interested in finding the minimum one. Fine. So how to do that? So since the basic idea is what is the problem state? Problem state is the multiple ways in which you can divide the matrices, right, into sub multiplication, smaller multiplications, and then find whichever is giving you the least amount of multiplication, total number of multiplication when you end up. So I can do multiplication like this. I can do the first multiplication like this, the second one like this, or I can do the first one like this, and the second one it's like this, only with itself. So multiple ways are there. Fine. So what we will do is how many possible ways are there? So the thing is we can put the parenthesis anywhere between these four matrices, right? We can put here, here, or here. Anywhere of the places we can put. Correct? The parenthesis. So our parenthesis would actually travel from your, I mean, the start to the n minus 1. That is the end. We can put it anywhere. And when we put it at any specific place, we would check what is the total number of multiplication required when the I mean the segregation is at that particular point. So that marker is used with a variable which we k, okay, and k would vary from 1 to n minus 1 because essentially you are adding it over here. There is no meaning of adding it before that. So it will travel from 1 to your n minus 1, and then the next step we will discuss now what happens. Okay, so if you see this matrix, so when we say you have to multiply the matrices, let's represent it in the form of numbering. So we had A1, A2, A3, A4, right? So I can tell you you can do multiplication like this, but let's represent it in the form of numbers. So what I mean is 1, 2, 3, 4, these four matrices we have to multiply. Assume all of these are matrices. So I can multiply 1, 2, and then 3, 4. I can multiply 1, 1. Now this is important. 2, 4. So I multiplied from 2, 4 at first, and along with that I am multiplying 1 with itself. Not 1 with itself. This essentially means that 1 is kept aside, right? So when I write A1, A2, A3, A4, what did we do? We had one option like this, correct? So this is basically this option. That 1 is kept aside. That's why I'm writing 1, 1, right? And then 2 to 4, whichever. So the left side of any ordered pair like this, the tuple, right? The left side means the matrix from which the multiplication starts. The right side means the matrix till which the multiplication goes. So if it is 1, 1, it means the multiplication starts at 1 and ends at 1. That means essentially you are not doing any multiplication. It's the matrix itself. Okay. So 1, 1, 2, 4, maybe another case. And then we have, let's say, 1, 2, 3, and 4, 4. Fine. So these are the possibilities that you can think about for doing matrix multiplication. So now see, if I see all of this ordered pair 1, 2, 3, 4, 1, 1, 2, 4, 1, 3, 4, 4, what is the common observation that you can give? The common observation is, since these tuples or ordered pair means from the left value matrix to the right value matrix, we are doing multiplication. So 3, 4 means from the third matrix till the fourth matrix we are multiplying, right? So if it means The left value is the starting matrix and end value is the ending, the right value is the ending matrix. That means the start must be always before the end, correct? Because starting of the matrix must be before the ending matrix. If that is the scenario, I can tell you that starting matrix, I mean the left value in the tuple or the ordered pair must always be lesser than the right value. Correct? I can tell that. So what does that mean? That the right value is greater. So if you see that in the form of a 2D matrix that we had, like in the other algorithms, right? If you see this behavior in a 2D matrix, right? Right? If you see the behavior, you would understand that all the value when the right value, when the right values are greater than the left value, that actually happens on the top part, that top right angular right triangle, the top triangular part of the uh, matrix, because the left diagonal, the principal diagonal, this diagonal, this the left diagonal. The left diagonal is the position where I becomes equal to j. I mean, I becomes equal to j. Okay, I becomes equal to j. The middle diagonal, the left diagonal. Okay, so any value which is below this, I mean this part, right? In this part, I is always greater than j. And the other way, this part, right? This part, I is always lesser than j. And this is what is more relevant with respect to our matrix multiplication, because if my tuple is I comma j, it essentially means starting from I matrix till j matrix. So I must be smaller. So I is smaller over here in this region. So we have to do the work in this region. And from there we have this idea of this table where this is kind of blocked, it's not required. But we cannot define a matrix like that. Matrices, 2D matrices would be a square structure, I mean, a rectangular structure, whatever. But this lower triangular part of the matrix is not required, still logical. So only the upper triangular part is what. Now, what is the number of multiplication required to multiply a matrix with itself, right? I mean, we are not multiplying the matrix with itself. Basically, what I mean is this thing, that when I'm keeping A separate, right? So only for keeping separate, I'm not even doing any multiplication. So no multiplication is required when 1, 1, 2, 2, 4, 4, like these terms occur, because that essentially means you are keeping it separate. No multiplication has been done. So 1, 1, 2, 2, 3, 3, 4, 4, I mean, in any form k, k, n, n, when I is equal to j, essentially is what I mean. Whenever that condition holds, then it would be equal to 0. The matrix multiplication matrix would store 0 because we did not do any multiplication. So the left diagonal is 0. This is the first initialization, which is important. Fine. So the left diagonal is made 0. Just a second. Yeah. Fine. So we set all of these to 0. This is the first step. Now we proceed till the to the next part of the multiplication. So now say let's assume A234 is something we are trying to multiply. So what does this means? 2 to 4, correct? 0, 1, 2, 3. Okay. We have to have another one. Fine. Now see, the idea is So the initialization 0, 0, 1, 1, 2, 2, 3, 3 and 4, 4 has been done. After that, which is the next value that we are trying to calculate? Let's say 2, 4 is the next value that we try to calculate. So where is 2, 4? So 2 and 4 is where? So this is the cell which we want to calculate the answer for. Okay, assume. So if this is the cell for which we want to calculate the answer, okay, so again this is for 5. Okay, anyways, so just consider this example. Here it would be actually for 5 matrices, but fine, no problem. So what I mean is just consider this matrix and consider that we have to find the solution for this cell. Okay. Now, what are the values required to find the minimum number of multiplications for this cell? Okay. So this means our multiplication from 2 to 4, correct? From in that respect, considering starting from 0, to make a little bit changes here. Just a second. Let's say this has been 0 to 1. Suppose this has been 0 to 1 and it is 2 to 3. Fine. So yeah, 2 to 4, what are the values required? So if I find which are the values required, right, to multiply 2 with 4, okay, so we would find that this is the cell that I need and this is the cell that I need. Why? 2 to 4 is fine, decompose it further. If I decompose it further, so 2 would be there, 3 would be there and 4 would be there, right? Now I can multiply 2, 3 first and keep 4 separate for later, or I can multiply 2, keep 2 separate for later and multiply 3, 4 first. Right? Again, for 2, 4 itself, I have two possibilities. Right? So if I write it in terms of ordered pair, what would be the thing? 2, 3 and 4, 4. Here also, what will I have? 2, 2 and 3, 4. Correct? So what is 3, 4? You see, what is 3, 4, right? So you see 3, 4 is this cell. And 2, 2 is 0, we know. So this is 0. Okay. So the other 4, 4 is also 0. That also we know. And the other one is 2, 3. So which is 2, 3? 2, 3 over here. So if we go over here, we get this. So I need the values of these two cells in order to calculate the value of this one. Why? Because 2, 4 is decomposed into two possible ways of matrix multiplication. And 2, 4 itself is a further subdivision of, let's say, we just modified the problem a little bit. 0, 1, 2, 3, 4. Fine. Okay. So yeah, this is the case. So if you see any of this case, let's pick this one. Okay, what is this one? It is 1, 4. Right? So write 1, 4. If you have to multiply 1, 4, what are the probable ways? First way is I can write 1, 1. That is, I keep 1 separate and multiply from 2 to 4. Or I can also do 1, 3 and keep 4 separate. Correct? Or I can do 1, 2 and keep 3 and 4 both of them separate. So for 1, 4 I have three possible, for 1, 4 which are the possible cells that I need? I need 1, 3. So where is 1, 3? 1, 3. That is this one. So for calculating this one, I need this cell's value. First thing. Okay, let's remove all this. Yeah. So to calculate this one, I need this cell's value. Then what is 1, 3 is done. So 4, 4 is there, 1, 1 is there. So this cell's value I need, this cell's value also I need. Then 2, 4 is there. So 2, 4, this one. So this cell's value I need, this cell's value I need, and then 3, 4 is there. 3, 4 we have marked. 3, 4. Yeah, this cell's value I need. Correct. And also we need the value of 1 comma 2. This one, which is 1 and 2. This cell. So basically, to find the value of this particular cell, we needed this one, this one, this one, and this one, this one, this one. So if you check this thing now, you see the pattern. You take any of the cell, let's say for this one, I need the value of all the cells from this cell till the middle diagonal. That is, I need the value of this one, and this one. And for calculating this one, I also need the value of this cell, because I have reached the middle diagonal here. Okay, so I need the values up to the middle diagonal in order to solve the ij value. Now, how to actually get that? How I am actually getting that? So I'm simply dividing, right? I'm just saying, simply putting the segregation bit of multiple matrices in multiple possible permutations. How the permutations I'm getting? I'm just segregating. I'm just putting a bar between a different position. Okay, and that means the first position is 1 and it's going till n minus 1. That is the end of the number of matrices. So we'll have a loop which runs from 1 to n minus 1, and that loop variable would be k. And then what I am doing? Now let's come to the recursive part. So if I denote the number of multiplication required by mm in a matrix multiplication 2D matrix. So when I write I comma j, it essentially means that the minimum number of multiplication required to multiply matrices from I to matrices j. Okay. So how many is required? So this is given by, I would need to multiply. So I have I'm doing the segregation, right? I'm putting the bar between different places of the matrix, which I discussed that 1 to n minus 1 earlier. Correct? I'm just segregating in that manner. So let's say I use the variable k to do the segregation, and that's why the first matrix that I would, let's say we have all these matrices over here, over here, so many matrices here, and at some position I put the parenthesizations. I multiplied this one and I multiplied this one, and this position is k, right? So let's say if this is the breaking, right, then how many multiplication would be required to multiply this M1 matrix with M2 matrix? I mean, after we do this multiplications, right, as interior of smaller multiplication, we would end up with a big matrix like this. And then over here also I would end up with a big matrix M2. How many matrix multiplication is required to multiply M1 and M2? Okay, fine. So that would be what? It would be summation of, so assuming the first index over here is A, and here it is D, and here it is T, comma C, right? Then the answer would be E, B, C. These many number of multiplication is required to multiply M1 with M2. Now M1 itself is a bigger sub-problem because it has multiple small matrix multiplication. These would again be broken down. This would again be broken down further into sub-problems. Okay, that we would come to later. So of I comma j essentially boils down to two matrix multiplication of I to k plus of k plus 1, the next one, till the end j plus the matrix multiplication, which is, let's say, my degree, right? I'm denoting with d, this ADC. Degree means the value of the matrices, the dimensions of the matrices, right? So let's say M1 matrix was dimension D0, D1, suppose. M2 had dimension D1, D2, like that. Fine. So I'm denoting it with D. So D of I minus 1, right? I mean, why I minus 1? If I'm denoting M1 with 1, D1, right? So I minus 1 with D0, that is the left, I mean the R cross C degree, right? So the number of rows, R. So this is for first matrix M1, I am denoting D1 over here, D0 cross D1. So it is D0 cross D1, right? For M1 it is D0, the left dimension. For M2 it is D1, the left dimension. That's why in order to refer the left dimension, I am writing Di minus 1 into D common, the dk, and dk into d. Okay, the only problem over here is that this k where to put I don't know, because in different ways I would get different result, and that's why the thing that you have to do is you have to put this whole thing in the over here minimum of k, minimum of this thing where you are writing, just a second. This is basically you find the minimum where my k, where k would be equal to 1 to n minus 1. That means I'm putting k at different places in between the matrices multiplication, right? Putting k at different places, let's say this one and this one. So that parenthesization is putting k at different places and checking what is the minimum among all of them, right? Whichever it is, I put in I. That's it, and that's what we do over here. If I go to this place, you check that once the so someone was asking on Discord that what is this tree line? This tree line is nothing but initialization. So you can also, so whenever we are going for minimum of some value, right, we have to actually initialize it with the maximum possible value, right? And in case of finding the maximum value, we initialize with the minimum possible value. So this is just that thing, this line. Okay, this line is just initialization. If you want, you can just put a very large value in place of this line. Just initialize your matrix with a very large value. Initialize the diagonal element 0. Do not change this diagonal element 0 condition. Otherwise, it would not work, right? This concept that every diagonal 0, 0, 1, 1, these things must be 0. So do the initialization like that. That put the primary diagonal element 0 and all other elements put it to be infinity, and then you do the reduction. Some big number, no problem. So this is basically initializing. In every iteration we are initializing it with the first elements value. That's it. Okay, if you don't understand this line, no issues. Just assume that you can put a max value in the initialization except the diagonal elements, and then just ignore this line. Now see the main part, and after here we are just using k and using the same formula that we discussed. The only thing to understand over here is these two lines, so these three lines actually. Yeah, these three lines. Then it's just nothing conceptual, but just traversing the array. So we discussed that we have to traverse the array in the way that we discussed, right? So in order to answer this cell, I must have values of this one, and this one, correct? Diagonal elements are already initialized. So we must, what is the order in which we actually should fill the array? So let's actually check that. What is the order in which actually the array should be filled? So as of now, just assume that the diagonal elements are filled up. Nothing else has been filled up. Right? Okay. So if you see that we would start the filling of this array. I mean, since we need a diagonal dependency, so you pick this cell. The dependency is like this. I need all these values. I need all these values. Right? Like this, I need all the. You pick this cell. I need all these values. I need all this. So this is the way in which these dependencies are there. So we would start filling the data in this manner. We would consider filling this cell first, then we would fill this cell, this cell, this cell, then we would come to this cell, because once we have these two cells filled up, now I can answer this cell, right? And like this. So this one, then this one, then this one, and then I move again to this one, and then this one. This is the order in which my array would be filled up. Okay, so this loop over here, if you just observe that it's adding, I mean, this part, this two loop, this is basically representing, simulating the same idea that you are starting a difference variable from 1 to n starting, and then you are simply moving it to 1 to n, and then you are simply adding that difference value. So if you see over here, in this row, in the first row, right, sorry, in the second row, which is index 1 row, how many places are you going towards the right? How many times you are going? You are taking 3 steps, right? 3 steps you are taking. What was the length? The length was 4, maximum length. So 4 minus 1, 3. So 3 steps you are taking to the right. So in the next example, 4 minus 2, 2 here, right? 4 minus 2, 2 steps you are taking. So the difference you are adding with the row value, and that much steps you are taking. So I plus difference. That must be your j. Correct? The now column number is I plus the difference. So that's what it is doing. Column number is I plus the difference. Okay. Just, I mean, you have to think about it a little bit. Unless you yourself think, you would not get the idea. But that's it. I mean, just you're trying to simulate the order in which we discussed the filling. You will fill this cell first, then this cell, then this cell, then this cell, then this cell. You would like fine. So that is done by this thing, this thing. And all other things are fine. This is the induction structure that we discussed, and then we are returning the values. Okay. So that was about matrix multiplication. Any doubt if you have, please ask. Matrix multiplication. Okay. So no doubts. Now divide and conquer. Some actually not very detailed. You are asking some of you have posted that divide and conquer was also something that we had doubts about. So very important part. If any one of you are there who want to ask about something specific in divide and conquer, it's fine. Otherwise, this part is important actually. A bit the quick select. This concept is very much important, and I feel that if some of you have doubt in this concept, let's discuss this first. You can pick up any other doubt which you have until that. Otherwise, I will do this at first. So fine. In divide and conquer in this quick select, what we are basically doing is see. So in quick sort, actually, we discussed that how to sort a given array, but the problem was its worst case time complexity was going to n square. Why? Because you are putting a particular pivot, assuming your pivot is such that it is being placed at one of the corners, maybe the starting of the array or maybe the end of the array. In that case, your sub problem, right? It's a divide and conquer approach. So you must divide the problem into sub problems. So the sub problem, in case your pivot is placed at the first or at the last of the array, is only reduced by size 1. In that case, you are basically applying a order of n partition algorithm by n minus 1 number of times, because essentially you are decreasing the problem space by 1 every time. So intuitively you can understand you are applying n times order n algorithm in minus 1 times, it takes order of n square time, and that is what actually happening, that you get quick shop's worst case time complexity to the order of n square. Correct. But if you can place if you can guarantee that maybe not at the middle, but at least at some ratio, some proportion, some ratio in between the array, we can place the pivot, right? So if this is the array, if we can guarantee that we can place the pivot at some position in the between, right? Somewhere over here, any place, right? Not at the extremum. Then we can guarantee that, okay, the asymptotic time complexity is in terms of order of n log n. But how to do that? So in order to address that issue, we would at first actually discuss another problem, and that problem is the question of finding the kth largest element in a given list or array. Okay, so as of now, just forget about the quick short. But for addressing that problem, we actually came with another problem, and that is finding the kth largest element. So you would argue that the simple way to find the kth largest element is sort the array, and just print the index of k, right? ARR k minus one. So and that's it. If you are sorting in a descending order, if you are sorting in ascending order, then you would print size minus k. Anyways, so that would take you order of n log n time by performing a comparison based sorting, like let's say merge sort or heap sort, right? Which can guarantee you n log n time. But can we do a better than this? That's the question. Now, what we will do in order to, so the question is to find kth largest element. That's the question. To find kth largest element. Fine. So what we do is we actually use the partition algorithm. Use partition in a different way. Fine. So what does partition algorithm do? Partition algorithm, given a array, let's say this is the array. Partition algorithm would choose a pivot. So let's say this is my pivot over here at the end, and it would place the pivot at its proper location in the array. So assume its proper location is over here. Okay. So now I am deleting this thing. So assume that the pivot has already been placed. Yeah. Now, when the pivot has been placed, what does partition, I mean, when you are placing the pivot, what does it mean? It means that this element is at least at its proper position. It is in the position, and in the same position, it would remain in the sorted list as well, and the list would be sorted, right? So this is in the correct position as it would be in the sorted list. So that means, let's say here you have X number of elements, correct? So that essentially means if this is at its correct position and all the numbers to the left of the pivot are smaller than the pivot, right? And all these, there are X number of elements which are smaller than the pivot, is essentially means that all these X elements would stay within this area only. Okay, and they are smaller than the pivot. Now, if I am asking you to find the kth largest element, okay, and let's say X was equal to 7, that is there are 7 elements over here, and I asked you to find the, let's say, fourth largest element. Okay, the question was to find the fourth largest element. So what do you understand now after applying partition, just random partition ones? You understand that there are 7 elements in the left side, and they would always be there in this part of the array all the time. I mean, all the time means it remains in the left side of the first pivot, which is placed over here. So that means the fourth largest element must be, I mean, assuming that we are sorting it in the increasing order, sorry, decreasing order. So the fourth largest element would be over here, right? Assume that the array is sorted in a decreasing order. So the maximum 7 elements are on the left hand side, and that's why the fourth largest element is also on the left hand side of the pivot. That thing I can guarantee. Now where it is, I don't know, on the left side. So what we do is we again call partition only on the left part. Okay. In quick short, our motive was to sort the array. So that's why even when we got the pivot placed at a certain location, we used that index to call quick short on both the parts, right? We called quick short on beginning to k, right? And whatever other values. And again, we called quick short on k plus 1 to end, whatever other values. And here we call the partition algorithm, right, with the matrices and all. and k was returned by the partition as the index of the pivot. So this was my quick sort. But here we need to find the element, not sort the array. And simply by putting the pivot, I can guarantee you if x is equal to 7, that is, if I write it in condition, if x is greater than k, that means, and if the array is sorted in a descending order, that means my kth, I mean the fourth largest element or my kth largest element is on the left side. But if x is less than k, right, that means if I just reverse this, if it is 7 and it is 4, sorry, 7 and if this is 4. So that means only 4 elements are there, correct? And those are the fourth largest of the elements because it's descending order. So this is the fifth largest element. This is the fifth largest element. Fifth largest. And whatever elements are left are over here, correct? So that means I need the seventh largest element, and essentially it means that my seventh largest element is somewhere in between this region. Correct? So I can simply discard this whole part. This part I would discard. So this helps me in discarding the subparts of the array, and I can only go to another part and then again apply partition, and that partition would again apply a pivot. So let's say I apply on the right part. So the next pivot is placed somewhere over here, right? Next pivot is placed somewhere over here. I get a value of this part, right? This part. Let's say this is equal to 2. Let's say this is equal to whatever some value, let's say 4. Fine, I get something like this. So I can understand now that okay, I knew that I have to go to the right side. Now depending upon the value of this pivot also I understood that whether I have to go to the left side or the right side. That is, I have to search over here or search over here. Now since I need to find the seventh largest element. Here the value was 4. This one is the fifth element, right? So seventh, where it would be? It would be obviously over here, right? 6, 7 plus 2. This is definitely the eighth largest. The pivot is definitely the eighth largest. Fine. So I know that I have to find over there. So now since there are only 2 elements, in one iteration I would find the seventh largest element. So this gives me a kind of log n kind of approach, because I'm every step I'm actually eliminating some part of the array to find the kth largest element. But again the problem comes, and that is what happens if in the partition, at the end of the day we are using partition itself, right? So what happens if the partition happens and picks the pivot which is at the one of the terminal position, at the extreme position. So even we use the partition algorithm to just search a kth largest element, but since it is partitioned, so end of the day we can again pick the bad pivot and end up with order of n squared time. So we do not get any advantage. So that's where we understand the concept of median, and that's where something which is new over here. And once you understand the median, we simply apply the median function in this partition function. The result is the quick select in an order of n time. We would discuss that. And when you apply median in the quick sort, just add the median code in the quick sort, and before calling partition, call the median. Then call the normal partition, then do the normal quick sort. So once you do that, you get an order of n log n time. Fine. Now what is median? So our doubt is we may end up with choosing a bad pivot, which is one of the at the terminal position. So rather what we do is we have an array, let's say like this big array. Okay, what we do is we simply break it up into elements of a constant size. Now conventionally, according to the literature, this has been taken to be a size of 5. So we do it with the size of 5. But the idea is you take it up to a constant size. That's the main idea. Fine. So let's take the example in this case again with 5 only, because that's what we have learned. So we divide the big array into sub arrays of size 5. Once it is broken up into sub arrays of size 5, what we will do is we will find the median element of each of this subarray explicitly, right? Now, the thing is, since each of these subarrays are of a constant size, or so to say in this example of size 5, even though it's a linear process and you do that linearly only, but still it is a constant time. It is not order of n, because you are doing the operation on a constant size subarray. So whatever operation you do, it is ultimately going down to be a constant operation. Fine. But the problem is that constant operation, order of one operation, on how many arrays are you doing, or how many sub arrays correctly. So we have divided by 5, right? The whole array. So if we have divided the array by 5 and if the array size was n, right? So we have got n by 5 arrays or sub arrays. And on this n by 5 sub arrays, we are performing the median finding, which is constant in this case because the subarrays are of constant size. So we write n by 5 times constant operation, which is order of n time. Fine. So dividing the array into subparts is basically taking the order of n time. But now, I sorry, not only dividing and finding the median of each of these subparts. Now what we do is we repeat this process again and again, and until we actually get to a single array, we find the median of this one, right? So we got all the median like this, like this. Let's give the median, let's give the median. So get all these medians. Let's say this median is A, B, C, D, E, F denotes the medians. Again, you would see whether the new list which I got by considering only the medians A, B, C, D, E, F, right? Is it equal to the size 5 or not? If it is equal to size 5, then you just simply find the median of that list and return. If it is not equal to size 5, then again you apply the same step of breaking down into multiple lists each of size 5. So again you break it down into multiple list of size 5. So this is one list A, B, C, D, E. And then this is a single value. Fine, no problem. So again you would find the median of this value. Some value x would be coming. And again this is f, right? So you, since this is less than 5, you find the median and then you return this median of x comma f is returned. So repeat this step unless and until you get a value like this. So if we just represented it graphically, and that is the famous representation which is already discussed. So if I break the, okay, let me go to the diagram only. Yeah. So you see that here we have all this 1, 2, 3, 4, 5. This all this vertical 5 lines, 5 nodes. They are actually constituted the original array. Now we have divided into 5 sub arrays and kept it like this. And this yellow value is the median of this whole sub array, right? So all of these, each of these sub arrays have their median value as colored yellow. And now we are again finding the median of all these yellow elements. Correct. So let's say we find the median, and that median is, let's say, this blue one, right? The correct middle one, just a graphical representation. So if you have this blue one as the median, now let's make some observation. What can we tell about this cell, right? This particular value. What can we tell about it, right? So that we can tell that, okay, so this value is above the median of its line. The median of its line is this one. So it is above it, and that's why we are considering from top the value is starting, right? So it is obviously lesser than its median. This median, right? This median, this value is actually lesser than this value, the median. Now this median is again lesser than the blue, the whole thing, right? Blue color, the the overall median, right? So this median is again lesser than the blue one, and this value is lesser than this median. So ultimately by transitivity, we can say that this value is actually lesser than this blue color node. Accordingly, if you apply the logic, you will see that all the nodes over here, just above this yellow line, they are all smaller than the blue one, and all the nodes over here, they are all greater than the blue one. Fine. So if I pick this blue one in the original array, then I can guarantee some elements would be always be smaller and some elements would always be larger than me. And that means how many elements that we are actually taking an assumption, since we have divided by 5, the subarrays are of 5 size. So you can just take the elements here. So among the 5, 2 over here are small, 1, 2, 3 over here are smaller, correct? So accordingly, we would have a factor of 3, and the other way, total 10 elements are there. So other way, we would have a factor of 7. So if you check over here, 3 by 10 and 7 by 10 are the two factors. Okay. So yeah, so basically you get a 3 by 10 of the total length as smaller and 7 by 10 as larger. That's the idea, and basic thing is these factors might change when you actually use not 5 or maybe some other constant value to divide the array, but the main idea is whatever be the factor, but it is a factor, and that guarantees some value is lesser and some value is more greater, right? Lesser and greater than the blue color node. And if I pick the blue color node, it would not certainly be the terminal, I mean, one of the extremum element. But that is fine. Now I can just get the blue color node and put it into the partition algorithm, and that would always give me a order of, I mean, n log n time quick shot in the by returning the median, by using the median of median. But now the question is, how much time does this median of median took? That we also discussed, that simply dividing by 5 would be an n by 5 number of subarrays and multiplied by order of 1 time, because finding the median of a constant size array is order of 1. So it again takes order of n time, n by 5 into order of 1. So order of n time is taken by median of median. Order of n time would be taken by your partition algorithm, and that's a win-win. Therefore you did not affect your time complexity, but it actually ensures that you do not end up with a bad pivot. So that's it, and then you actually apply the quick simply partition algorithm. Now partition algorithm can be applied in 2 different ways, and that's what has been discussed in this week. The first way is to answer the question kth largest element, and the second way is the quick shot. Now what is the difference between both of this? Here we call basically, here what we do is we call the partition, okay, any partition is called only on one subpart, and here partition is called on both subparts. Fine. So that's the difference. Now what is the condition? If you want to go to the code and check about it. So this is your quick select. You see that if you see that this one, this is the on the, I mean this is partition applied on the kth largest element. So if you see that k is less than the length of the lower part of the array, right? We discussed that. If k is less, this lower length is basically the x in our example over here. This x, right? This one, this x. So if k is lesser than the x, right? I mean this condition. So that means your element is residing in the x part. Okay. So that's what has been done also. That is, you apply L2 lower. Okay, I mean depending upon it is descending order. Sorry, not L2 lower. It's lower to k. So basically, depending upon whether you are applying ascending ascending order or in the descending order, on that it happens. So if you are applying in ascending order and finding the kth largest element, you have to go to the right, and that's how you have to search it. So you do that, you apply L2 lower, and otherwise if it is in the other direction, then you apply lower plus 1, just like binary search. But when you would return the value, right, that is fine, but the returned value, when it would happen. So if I check over here, so if this is my array and this is where the pivot has been placed, my case, that is, I want the fourth largest element, and the number of element here, which is x equal to the, suppose say 3, right? So I know that I have 3 elements over here, and I want the fourth largest element. So this element is obviously the fourth one, right? Fourth largest. This is the smallest element, then large is the fourth largest. Fine. So whenever you have the left subpart just one less than the k value, that is k equal to the size of the left subpart plus 1, right? So that is the element which you have to return. If I go over here, you check the lower length plus 1 is equal to k, then you return the value, and that is the k largest element. Fine. So that's it. And when you have to apply the fast select, I mean, this is the kth largest element function, right? So when you have to apply that on the right part, not on the left part. So the condition when x is, or in this case, the lower length is actually lesser than k, right? If that is the condition, this condition, right? When lower length is lesser than k, in that condition, what you have to do, since you are going to the right part, you have to subtract the length of the left part from k, correct? Otherwise, when you are going on the right part, you would start the partition just on a new sub array, right? Just considering it as a new sub array. So if you try to find the k, the initially whatever k value was given, so let's say 4, so fourth largest element, then it would not be correct, because already few elements are already there before it, correct? So you must subtract the length of how many elements are there before it, right? So that is done over here, k minus length of lower plus 1. So the number of elements which are before the right part. How many elements are before the right part? The length of the lower, I mean the left part plus the pivot itself. So the length of lower length plus 1 for the pivot. Those many elements are already there on the left side. I am searching on the right side. So on right side, I would not search for the kth largest element. On right side, I would search for the k minus lower length plus 1, lower length plus 1th largest element. Okay, so that's the point. So only difference of what we are using here is we are using simple partition as before, and only thing is we are adding this median of median function, and then we are calling the partition. But in case of finding this kth largest element, we are applying this fast select method on only one hop. So you have if condition. So if this, then you apply on this hop. Otherwise, you apply on this hop. In case of quick shot, up till this thing, up till this line, it would be same, right? From top to this much would be same. Only even this would be same. Only thing is these conditional things would not happen. It would be much more easier. What we would write is simply quick shot L to K, and then K to K plus 1 to upper. Right? And here we are not doing that. Here we are only calling out one of the half depending upon whichever condition is satisfied, whether else or whether it. So that is fast select and quick shot. Both of them, they use the median of median method. Fine. Okay. So I mean, that's the basic thing which you all told to be discussed on this course. If there is something else you can tell, maybe in the next session we can discuss about that. And regarding the quiz questions discussion and all, we would do that in the next, in the revision sessions and all, we would do that along with the revision session. All the questions we would discuss. Fine. Okay. And sir, can you suggest any other important algorithms for the OPT? So in the chat, someone has written, fine. Important algorithms means I initially told you guys in the previous session, graph algorithms are important, not only over in the exam. It's important in any exam, in any part of your interview, everywhere else graph algorithms would come, right? So accordingly, we have also given importance to graph algorithms. Other than that, everything is a bit balanced only, no problem. I mean, just be very clear with the basic algorithms. Okay, you might not have done a lot of difficult codings or multiple application of different algorithms, but you should be thorough with the basic algorithm and all the algorithms. Okay, just the skeleton of each of these algorithms you should be clear with. Fine. Okay, so thank you all. We would discuss all those things in the revision session about the quiz questions and all. Thanks a lot.
Thank you.